cũng hơi dài hơn một chút. Một số các cái bạn sinh viên ở trường sư phạm Hà Nội 2 hoặc là các bạn thậm chí ở trường khoa học tự nhiên cũng có thể chưa biết về giáo sư Trần Vĩnh Hưng. Thế thì về giáo sư Trần Vĩnh Hưng thì giáo sư Trần Vĩnh Hưng là học ở hệ cử nhân khoa học tài năng ở trường Đại học Khoa học Tự nhiên Đại học Quốc gia Thành phố Hồ Chí Minh khóa năm 2022-2026. Sau đó thì giáo sư Trần Vĩnh Hưng làm luận án tiến sĩ tại trường Đại học California ở Berkeley, một trường đại học rất là nổi tiếng, chúng ta nghe đến thế chúng ta cũng đủ ngưỡng mộ rồi đúng không ạ? Trong giai đoạn từ 2008 đến 2012 thì ngay sau khi tốt nghiệp hoàn thành luận án thì giáo sư Trần Vĩnh Hưng đã làm thực hiện những cái công việc ở các cái rất nhiều các cái đơn vị nghiên cứu nổi tiếng, như chẳng hạn như là từ năm 2012 đến 2015 giáo sư Trần Vĩnh Hưng là Diction Instructor ở khoa toán của trường đại học Chicago. Và từ năm 2015 cho đến nay thì giáo sư Trần Vĩnh Hưng lần lượt là trở thành là Assistant Professor, Associate Professor và Professor ở trường đại học Wisconsin ở Madison ở Hoa Kỳ. Thì giáo sư Trần Vĩnh Hưng cũng là cộng tác viên thường xuyên của Viện Nghiên cứu toán cao cấp, và từ tháng 2 năm 2022 đến nay thì giáo sư Trần Vĩnh Hưng là thành viên của Hội đồng khoa học của Viện Nghiên cứu toán cao cấp. Thì lĩnh vực nghiên cứu của giáo sư Hưng thì là về phương trình tạo làm riêng. Giáo sư Hưng cũng đã đạt được rất nhiều các cái thành tựu trong khoa học, đặc biệt là nhận được rất nhiều các cái quỹ nghiên cứu danh giá của Hội toán học Mỹ, quỹ nghiên cứu NSF liên tiếp trong rất nhiều năm. Giáo sư cũng hiện nay giáo sư đã viết 2 quyển sách. Đó là một cái quyển sách về nằm trong cái series Lecture Note in Mathematics. Cái này là dựa trên những cái bài giảng của giáo sư Hưng và giáo sư Lê Quang Lẫm ở Viện Toán cao cấp, nếu như mà tôi hiểu đúng là như vậy. Và một quyển sách riêng về phương trình Hamilton-Jacobi, lý thuyết và ứng dụng. Ngoài ra thì giáo sư Hưng cũng đang hoàn thành một cái bản thảo về một cái quyển sách với một giáo sư ở trường đại học California ở Irvine về một a course on weight KMA theory. Giáo sư Hưng đã công bố rất nhiều các cái công bố ở trên các cái tạp chí khoa học thuộc dạng là danh giá và top 5, top 10 trên thế giới trong toán, chẳng hạn như là ở đây có thể kể ra như là các tạp chí như là IMRN, GTE, GFA, MathRNN, SHAM, Transaction và AMS, đặc biệt là CPAM, Indiana Journal Math, Annals of Math, Advanced of Math, Canva, vân vân, rất nhiều tạp chí nổi tiếng. Giáo sư Hưng cũng là một người mà tôi rất khâm phục ở cái bên cạnh cái công tác nghiên cứu khoa học tốt thì giáo sư Hưng cũng là một người mà rất tích cực trong việc là đào tạo thế hệ trẻ. Cái này tôi khẳng định có thể là cái ý kiến cá nhân của tôi, nhưng mà điều này có thể thể hiện rằng là qua những cái việc như giáo sư rất là tích cực trong các cái kết nối với cộng đồng toán học ở Việt Nam và thực hiện các cái bài giảng liên tiếp ở trong nước, chẳng hạn như là một cái rất là điển hình, đó là giáo sư Hưng là cùng với giáo sư Lê Quang Lẫm là thực hiện cái seminar toán học và chương trình gặp gỡ mùa hè, mà tôi nghĩ không biết là cái tên gặp gỡ toán học ở đây có hứng từ cái tên gặp gỡ mùa hè của giáo sư Hưng hay không. Thế thì và giáo sư Hưng cũng có một cái series blog ở trên YouTube gọi là series toán không màu. Nếu mà các bạn sinh viên chúng ta hoặc là các bạn học viên quan tâm có thể xem xét ở đó, thì cũng có thể thấy là ở đó giáo sư Hưng phỏng vấn rất nhiều các nhà toán học nổi tiếng của Việt Nam để trao đổi về những các vấn đề về toán học. Giáo sư Hưng cũng hiện đã hướng dẫn 6 nghiên cứu sinh, đang hướng dẫn 6 nghiên cứu sinh, và đồng thời là editor của một số các cái tạp chí khoa học, chẳng hạn như là Minimax Theory and its Application, rồi là Advanced in Continuous and Discrete Model, và editor của cái chuỗi các cái bài giảng toán học Lecture Note in Mathematics của nhà xuất bản Springer. Có lẽ là cũng không lắm làm chiếm nhiều thời gian của giáo sư Trần Vĩnh Hưng cũng lâu, Nhưng mà tất cả chúng ta nếu mà ai quan tâm thì có thể vào trang web của giáo sư Trần Vĩnh Hưng, ở đó thì có rất nhiều các thông tin mà giáo sư đã chia sẻ trên đó. Thì hôm nay tôi rất là vinh dự xin giới thiệu giáo sư Trần Vĩnh Hưng sẽ báo cáo về decision progress on the study of a critical coagulation-Fragmentation equation. Chúng ta xin mời giáo sư Hưng. Mời Hưng ạ.
Cảm ơn anh Thạc Dũng ạ. Em cũng chân thành cảm ơn ban tổ chức và mọi người đã tạo điều kiện cho tôi được báo cáo. Tất nhiên là tôi cũng hy vọng là sẽ có lúc nào đó được đến thăm Đại học Sư phạm Hà Nội 2. Thì trước khi báo cáo thì tôi cũng muốn nói hai cái điều nhỏ nhỏ, nó cũng đơn giản thôi, nhanh thôi, để sau tôi phải báo cáo. Thì là thứ nhất là đúng là có lẽ Việt Nam mình là có rất nhiều những cái hội nghị toán học có chữ gặp gỡ. Gặp gỡ ở đây nó rất là thân quen, tức là người Việt Nam mình rất là nồng ấm. Tôi cũng hy vọng là những cái hội nghị này nó sẽ tiếp diễn được rất là lâu dài. Cái thứ hai là tức là hồi xưa tên của tôi là Vĩnh Hưng, tại vì bố của tôi làm việc ở Vĩnh Phú với lại Hải Hưng, nhưng mà thực ra bố tôi làm việc ở nhà máy Z121 thì nó là Phú Thọ cơ, chứ không phải Vĩnh Phúc. Bây giờ thì để tôi báo cáo thì tôi xin phép được nói chuyện bằng tiếng Anh để cho các cái ngôn từ nó được được rõ ràng hơn. Và tôi cũng sẽ cố gắng nhanh gọn để đi đến những cái chi tiết và những cái ý tưởng quan trọng, thay vì nói rông dài. Xin phép mọi người, nếu mà mọi người có câu hỏi hay là có vấn đề gì trục trặc kỹ thuật thì cứ nói ạ. Thì tôi sẽ nói về cái phương trình. Ok. I'm gonna talk about coagulation fragmentation equations. Let me go to the picture right away, and then I'll come back to the equations. Basically, this equation is sort of an equation that has two effects. That's coagulations, meaning combinations, that sort of groups of things come together with certain rate. For example, you can see that here on the left panel, that, you know, like, for example, like a group of one particle comes with a group of two particles at some rate to create a group of three particles. So that's coagulations. And then the other process is called fragmentations. Fragmentation does the converse thing, essentially, that you have a big cloud. At some rates, it's being broken into two smaller clouds. That's fragmentations. There's a famous Vietnamese story related to this, right? It's cây tre chăm đốt, with, you know, the first one, coagulation, is like khắc nhập, and the other one is khắc xuất. So this is a process that is a very complicated problems, that given a bunch of densities, and as time goes, you have things combined together and then things split. You can imagine that this is a problems with clouds on the skies, with clouds coming together, and if it's big enough, it might be split, and so on and so forth. And we want to understand the evolution of this problem. Okay, let me go back to the equation very quickly, and then I'll be more precise. You can have this is the equation I highlight here, where rho represents for the density of particles. So you have the density of particles, and you know, you try to understand how does this sort of density behaves, right? And you have two terms. The first term represents for coagulations, as I said. It's the binary merging, that if cluster of psi x meets with cluster of psi y, you create a cluster of psi x plus y with some given rate, let's say a of xy. That's given. And then vice versa, you have binary splitting, that you have a cluster of psi x is being broken into cluster of psi x minus y and y with also a given rate b. Okay, so that is a model, and then we want to see how do we model it. All right, so now let me talk a little bit about how do we write down the kernel, the coagulation and fragmentation kernel. It might look complicated, but it's a very simple, you know, like binary problem, right? So you can do it by simple combinatorics, like, you know, just a basic counting problems. You count, okay, you see, how do you create a cluster of psi S? Well, I mean, to create a cluster of psi S, you take something of smaller sizes, right? You take cluster of psi Y combined with S minus Y to create cluster of psi S, okay? So you can see that in this formula here, for a given Y, I'm taking cluster of psi Y with the density rho multiply with cluster of psi S minus Y with density rho of S minus Y. And this happens with a given rate A, okay? So I take this product that gives me the chance to create cluster of psi S. And then this happens for all Y. So then this is a continuous case. I'll also tell you about the discrete case. The continuous case, and I'm just integrating them from 0 to S. And again, here I'm doing double counting, right? Because Y and S minus Y is being double counted. That's why I have to divide by 1/2. Okay, so this is the first term. Next, you're gonna see that, well, I mean, not always that you can keep everything, right? You also lose cluster of psi S because it's gonna come, you know, together with cluster of psi Y for any Y to create a cluster of a bigger size. And then this happens, you know, with exactly this rate, rho of ST times with rho of YT, and with this rate ASY, and you integrate it because you can lose everything. You know, you can take any cluster of psi S combined with any cluster of psi Y for any Y, and that's why you have to integrate in Y from 0 to infinity, okay? And then this gives you the so-called the coagulation term. Coagulation terms here represents for exactly how much do we gain, you know, how many cluster of psi S do we gain, and then we have to subtract how much do we lose of cluster of psi S, and that's the coagulation term. Okay, and then similarly you can write out the fragmentation terms. You know, again, as I said, coagulation terms corresponding to khắc nhập, and then coagulation term, fragmentation term corresponding to khắc xuất, and as a result you write out the equation as the combination of two terms. And you can see, let me write out also the discrete case. This is simpler to see, right? In the discrete case, you can describe things in exactly the same way for the coagulation kernel. To create a cluster of psi n, you take cluster of psi y and cluster of psi n minus y, and then you sum them up to have this first term. Okay, that's how cluster of psi n is being formed. And then the second term that we have to subtract this because we take a cluster of psi I combined with cluster of psi n to create a cluster of a bigger size. So we have to subtract it. And same for the fragmentation term here. What is amazing and important about this thing that I want to bring up is that you look at this problem 2 here. Well, this is simply a countable system of ODEs. It's extremely strongly coupled, I mean, between all the ODEs, but this is a countable system of ODE. What is hard about this problem is that, I'll tell you, but is that the kernel A and B can be complicated. So the ODE is being strongly coupled. And the reason why I want to say it is because, you know, Vietnam, we have a lot of groups that are strong in ODEs, right? So this is an interesting countable system of ODE that might be of interest. Okay. So a brief literature, the coagulation fragmentation term is well known. I mean, without fragmentation, this is Smoluchowski equation that was written down 100 years ago. And then there are a lot of big names, a lot of top experts working in the fields that the math theory was only developed in the 1950s. And until now, there are a lot of important works, you know. For example, John Ball was the one who wrote down the rigorous theory for the infinite system of ODEs in the 1990s. He visited, you know, Vietnam like 2-3 years ago, right? So this is a very rich field with people using tools from analysis, from PDE, from functional analysis and probability. I wouldn't have time to go into all of this today, but I'll try to tell you something interesting. Okay. All right. What is interesting here is the fact that this problem is interesting. The reason why people study it is first it came from physics, but also that you know, this fun fact is important, and it's the point that you can see that because of the coagulations, if you have the combination force is going so strong, right? You keep forcing things to combine, merging together. Then after some finite time, it's like tofu, right? You start with grinding the soybeans, put them in water, and then, you know, all the molecules, the materials start sort of combine together and give you tofu. So that's something called gelation, meaning that because the coagulation is so strong that it forces things to combine so fast together that after some finite time you have gelation. You have some cluster of infinite size formed. And then same for cheese, or same for, let's say, you know, like other things, right? And also there's something in the reverse way, is something called dust formations, is that if you have fragmentations, the forcing things to, you know, to be divided so quick that after a finite time, things becomes, you know, tiny, so small, right? Things become zero size. So that means that you're also losing something. Either something is infinite, you know, the tofu, the cheese it's out of the system. You have something like of zero size, it's also out of the system. So this equation is extremely interesting in the sense that, you know, sometimes after a finite time you lose mass because of the strong coagulation or fragmentation. Okay. So in this this talk, and I have worked on this field for 5 years. I have always been focusing on this case. It's called the critical case. I'll explain why. Here, A S times S hat is sorry, A of S hat is S times S hat, meaning that when S is small, you know, if the two cluster is very small, the chance for them to meet is very small. I mean, you know, it's not much. But then when the cluster are so big, you can see that, you know, if the clusters S and S hat are extremely big, then the chance for them to meet is getting huge, right? Because you know, they can see each other almost immediately to form something big. So this is kind of an important kernel. And people in physics find it because they use scaling analysis. They see this sort of scaling and they can see that this kernel is very common. And B equals to 1, meaning that constantly, at the constant rate 1, that your thing being divided into 2, right? So it's a constant rate. And this is critical because you have the coagulation effects and the fragmentation effect. Sometimes one dominates the other, then it's easy. But in this case, they are of equal length. So, I mean, none is dominated. So, I mean, they are competing with each other, you know, like just competing with each other. And we want to understand this critical case. Okay. Now, this is a slide for PD persons, but I will explain to you very quickly what it means. Is that normally when we study the equations, sometimes it's very hard to look directly into the equations, and we would try to formulate something called weak solutions. Here, by weak solution, I mean simply that you try to use test functions to plug in and see how it goes. But this problem is very meaningful. You can see that what we measure here in this formula is very clear. I multiply rho with a test function phi. So I take the integral here and I measure the change in time, right? So I just take d over dt of the change. And you can see that it equals to the two terms down here. And the meaning of the two terms down here is clear. The first term is what? This is corresponding to coagulations. You take a cluster of psi s and psi s hat to form a cluster of psi s plus s hat. So in the system, you lose those two, right? You lose two small clusters. S and S hat, and you gain the cluster of S plus S hat. So that is very clear. That's the coagulation term. And fragmentation term is the last term here. It goes in the reverse direction, that you take, you have the minus signs here, so you lose a cluster of psi S and you gain cluster of psi S hat and S minus S hat. So although that normally for PD using weak formulation of solution and such is complicated, but in this case, in this specific case, it's very natural. You can see, you know, each of the terms here corresponding to what right away. It's very natural. Okay. And okay, now that we write this formulation down, we ask ourselves, how do we make use of it? And it's not easy, but I mean, again, I think that Vietnam, we have quite you know, strong foundations of mathematics, at least for middle school, I would say, or high school. You can see that when you see this kind of thing, you see that I have the function phi that is of my choice. I have something like phi of S plus S hat minus phi S minus phi S hat. And I want to get something nice out of it. And a very natural way to get something nice out of it is to take phi to be polynomials, right? Why? Because if you take polynomials, then you can use all the nice identity that you know, the Newton identities and all these identities to cancel things out and to have things nice. If you take phi to be like sine or cosine function, there's no way to cancel things out, right? So I mean, a natural way is to take phi to be polynomials. You will see later, but let me say it right away that if I take this function phi to be S, so it's to be linear, ps to be S, and you see that this cancel out and this cancel out. Okay. And by the way, I mean, for rigorousness, I need to take phi to be bounded, but anyway, let's ignore that. Okay. So indeed, now let's talk a little bit about the meanings of the terms. And in physics, right, I mean, people typically look at the moment, the kth moment of the problems. What I highlighted down here. For example, if you take k to be 0, so s to the k is 0, is 1, I'm sorry, then m of 0 is the integral of rho ds, which is nothing but the total numbers of particles, right? So the 0 moment is the total number of particles. And the first moment, when k is 1, m1 here is nothing but exactly the mass, total mass of the system. Why? Because I take the number of particles of psi s, right? I multiply with s, that gives me the mass. And then I take the integral, right? So m1 is the total mass of the system. So you can see, as I said here, if I take phi s to be s, you see that this terms goes to 0. They cancel out, right? So formally or heuristically, this is not true, but heuristically, if you take phi s to be s as a test function, then you see right away that the left-hand side is 0. 0 means that you have conservation of mass, okay? However, as I said, this is a heuristic argument because phi of s equals to s is not bounded. So, you know, we have to be careful with the thing we do. But anyway, this is sort of like a sort of a good good argument for you to see why taking phi to be polynomial is useful. Okay. And now we can try, as I said, to take you can say, well, you know, phi s equals to s is unbounded. How about I take some other simpler test functions? I can take phi s equal to 1, right? If I take is equals to 1, then I can measure what is M0. That's exactly the total number of clusters in the system and see how it goes. Okay. So if you take phi of s to be 1, then you have the left-hand side is this term, is the M0 prime of t. Just measure the change of the total number of cluster. And the right-hand side, you can trust me on this because, okay, I can go back. So if you take phi equals to 1, then this becomes minus 1, and this becomes 1. Wait. Minus 1. Both of them becomes minus 1. Okay. So you you plug it in here, you have this equals to is equals to this term here, right? And now you can use Fubini. That the first terms here is nothing but exactly the integral of s rho s ds square, right, by Fubini. So that gives me minus 1/2 of m1 square. And the second terms is give me 1/2 of m1, right? So as a result, both of them gives me these terms. And this is why I said that the system is critical. Critical because the coagulation terms give me minus 1/2 of m1 square. And the fragmentation terms give me 1/2 of m1. So none of them is bigger than the other, right? I mean, essentially I have to combine what the balance between m1 square and m1. It's just a basic algebra problem. You can see that I comes to this term down here. Now I can do a simple analysis on this, right? I see that assuming that the mass is conserved in the system, okay, assuming that the mass is conserved, I mean, as long as I don't lose the mass, then I can see that if m1 is greater than 0, greater than 1, meaning that this one is strictly less than 0, right? It's a fixed constant, strictly less than 0. So what does it mean? It means that I have the number of cluster in the system, sort of like at the beginning I have a lot, but then it sort of keep decreasing after some finite time, and then it becomes 0 or negative, right? Then what it means is exactly this is when coagulation happens, when a cluster of infinite size happens, because I'm losing all the cluster to form something infinite, okay? So that says that heuristically, if m1 is greater than 1, then I should lose all the mass. And on the other hand, if m1 is between 0 and 1, well, this is a positive number. So it just tells me that the number of clusters is increasing, right? I mean, it's increasing to infinity, meaning that, you know, things are being broken to be smaller and smaller, but seemingly I don't lose anything. So by this formal computation, people figure out that maybe m1 0 equals to 1 is believed to be the critical mass. And this was a conjecture made by physicists and also by the very influential group by Escobedo, Laurensois, Mishler, and Peckham, that they made the very sharp conjecture that you know, if the total mass in the system is smaller than 1, smaller than equals to 1, then I have the unique mass conserving solution, meaning that I'm not losing any mass. But if the initial mass is bigger than 1, then, you know, then I would lose mass after some finite time. And this is reasonable because you can see that if I have a lot of things in the system, then the tendency for them to form big cluster is high, right? And then when they form big cluster is high, they meet each other a lot more to eventually form a tofu, right? But if the initial mass in the system is not much, then, you know, they not gonna have a lot of chance to meet each other, and then they will stay like that for infinite amount of time. And this was a very important conjecture made by physicists and mathematicians. There was some partial progress done by Banaxiak, Lam, and Laurensois, but so far it wasn't to the end because they use moments method by using exactly what I told you, by using polynomial and then inequalities. But in this case, inequalities are not sharp, so you cannot go to the end. And there needs to be a different approach, and this is a approach. And this is where I came in, starting from 2019. Okay. So now let me switch gear to tell you something about some interesting things about our results. I will not have time, I think, to explain the details, but I'll tell you about both the continuous case that we have done in last 4 years, and then yesterday I just posted a paper on the discrete case that we finished after getting stuck on that for more than 4 years. So the point here, what is interesting is that instead of using, you know, this we learned, it's not our idea to use the transform, but I explained to you here. that, you know, the idea is here that people suggested that maybe it's useful for you to use polynomials. But we figure out that instead of using polynomials, maybe it's more natural in this case to use, you know, you can describe it as a combinations of polynomials, or you can think about the function phi of s is 1 minus e to the minus sx. This function is nice because first phi of 0 is 0. Second, for x and s positive or non-negative, this function is always bounded. So it's 0 and then always bounded. It's not like going to infinity. And we define the function s through this transform. This is called the Bernstein transform. So for those of you who have taught ODEs or who have used this, you can realize that without the 1 here, I can have this is the Laplace transform. If we have taught our students using Laplace transform to solve ODE, this is that, okay? And what is fantastic about this test function is that I can simplify this. You know, because as I said, right, if you have polynomials, you can, if you take phi to be polynomial, you can also simplify this. But what is remarkable about this test function is that if you take phi of s plus s hat minus phi s hat, by simple computation, it turns out that it becomes these terms. And this term is good because you can see that we have been able to write a complicated you know, combinations of 3 terms into the product of Vs and Vs hat. So this is going to help us to simplify a lot of things. And this is a fun problem I often met. You know, we have all solved a lot of Phương-trình-hàm in when we were younger, right? This is one of the simplest Phương-trình-hàm that you can see, that if you give this problem, you know, find any function phi such that you have this property. And in fact, I tried because I was hopeful that I can find some other magical functions to solve the problem, but it turns out that the function I have shown you is the unique one that satisfies this beautiful property. You know, going from addition, subtraction to be multiplication. Okay. So now let me show you that what does this transform do. Okay, this slide is complicated. I'm sorry. Okay, but let me explain it with you. So okay, what is my background? My background is that I am working in nonlinear PDEs, right? And one of the important direction I have been working on is Hamilton-Jacobi equation. What is fantastic about the problem is that we started out with some kinetic type equations, coagulation-fragmentation equations, that has nothing to do with what I know. But then after this magic transformations, this was first actually figured out by Menon and Pagel, that if you do these transformations, you can end up with the Hamilton-Jacobi equation. So let me show you very quickly what it means. So I plug in here. So you take phi to be the test function to be 1 minus e to the minus sx. You plug in the weak solution form. You have 2 terms here. Okay. The first terms, as said, you can write as a product of 2. Okay. And then the second terms you can simplify. This is, you know, this is simpler than you know, than the entrance exam to university in Vietnam. We can just do it. If you plug this one in, you can see that the first terms here becomes just this, and the second terms become this. So okay, let me bypass these calculations. At the end of the day, you end up with a Hamilton-Jacobi equations, okay, like this. And our goal is that we assume if the conservation of mass holds, if this holds, then I can write, if m1t equals to m, then I can write down the equation in the closed form. I have this beautiful Hamilton-Jacobi equation, and I know that, you know, the experts doing Hamilton-Jacobi equation from Đại học Sư phạm Hà Nội 2. right? So with this Hamilton-Jacobi equation, then the point is that I can analyze this Hamilton-Jacobi equation and use it to come back to give conclusion to the original problem. So I'm doing a complicated transformations that leads to a closed form PDE, right? I start with a system of ODEs. I do transformation to get one PDE. And then from the PD, I analyze the solution and I come back to read up information about the coagulation fragmentation equation. Okay, so let me go very quickly on the results because I'm out of time very soon. So this was our first paper in this direction with Trường Sơn Văn, who is working at Fulbright now, Fulbright University now. So what we shown is that if the mass is from 0 to 1, then the Hamilton-Jacobi equation has a unique solutions. And as a result, because it has a unique solution, we imply that the coagulation fragmentation equation has at most one mass conserving solution. So this is itself is already new because amazingly, the Hamilton-Jacobi equation, when it has unique solution, it implies that the earlier one, the coagulation fragmentation, has at most one mass conserving solution. So uniqueness is done. And then if the mass is bigger than 1, we shown easily, this is easy, that the equation, the Hamilton-Jacobi equation doesn't have a C1 solution. So it does not have any solution, smooth enough. And because it does not have any solution, you come back to the original equation. Then you conclude that if the mass greater than 1, there's no solution. And this is totally consistent with the conjecture. Okay. So the mass greater than 1 is totally done. The mass smaller than 1, we have only shown that we have uniqueness. What turns out to be hard is the existent result. I'll explain why. So in PD, normally existent is easier than uniqueness, but in this case, in fact, uniqueness is easier. Existent is hard. Okay, existent, we have only been able to show for the range from 0 to 1/2 that we have existent. That if we assume that the mass is between 0 and 1/2 and some second moment bound, this is allowed. I mean, then we have that the coagulation fragmentation has a unique mass conserving solution in a weak sense. And then in the paper that we just posted yesterday, that in the discrete case, it turns out to be much harder. Then we could obtain that we have the strong solution in this range, but I don't have time to talk about the discrete case. I just wanted to bring it up that the discrete case corresponding to a countable system of ODE. And as I said, I mean, Vietnam has very strong groups working in ODE, so maybe it's worth checking this out. Okay. So let me explain. Now I have, let's say I have 2-3 more minutes, but let me try to end soon. That let me explain why is it that it's hard to obtain existent results. Because you look at this, right? I mean, we have to pay some price when we do the Bernstein or the Laplace transform. What is remarkable about this transform is that you can see that you start with just a density rho. Okay, you do this transform, rho can be just exactly a density or just be a measure. But because you do this transform, you can differentiate your function in X how many times as you like. You can differentiate a lot of time that you like. And as a result, f is a smooth function. Okay. And it satisfies this sort of property down here. So not only that it's a smooth function, but it has to satisfy some sign changing property. And again, I mean, we have experts working on Hamilton-Jacobi equations. We know that this is a first order equation. Typically, the solution is only Lipschitz. Proving that the solution is smooth is very hard. And we have to use the structure of the equations. It's not that simple. And there's a hidden beautiful structure in this sort of model that make it works. Okay. So because I'm out of time, I'm just gonna say each of the slide in 5 seconds. So to do this, we first need to add something called viscosity. And then we need to show that the solution is C11. This is the hardest step. Okay, so we add viscosity and we show that the solution is uniformly C11, and then pass the limit, the solution is C11. Okay, let me ignore this. After proving that the solution is C11, then we can use characteristic methods, because this is the first order equations, to bring it from C11 to C infinity. This is hard, but standard. I mean, it's doable. And the last step is that we need to use some maximum principle, and we have to go along characteristics to show that the solutions satisfy this sign changing property, that if you differentiate n times, then it has the same sign with -1 to the power n minus n plus 1. So this is very complicated, but I mean manageable. Okay. So I would say that the hardest step is to prove that the solution is C11. Because again, normally it's only Lipschitz, but because of the special structure of the equation, we can do that. Okay. All right. So I'm sorry that I have to skip the details, but the time doesn't permit. So let me conclude by the last slide is that, in fact, the problem is quite well understood, you know, for the range m greater than 1, for the range 0 from to 1/2 is also well understood. What is missing is this range from 1/2 to 1. And then again, the discrete case is harder. We have been able to do it, but there's still a missing range. And then this is just the beginning. I think that this is gonna bother me for maybe a couple more years down the road. Anyway, let me stop. Thank you a lot for your kind invitation and attention.
Okay, so thank you, Hưng, for your interesting talk. So if there are any question or comment? Okay, I think there's no question, but could you please go back to the definition of the weak solution?
Sure.
I have.
Yeah.
Yeah, and before last slide, you give you choose a specific rate function. I mean, can you go back one slide? Yeah.
Yes.
So I my question is that you work on that kind of rate function. So why do you choose it? And if any possible to work on the other function? Yeah.
Yes.
That's my question. Yeah.
Yeah, thank you. Yeah, that's a great question actually. So basically, the reason why, as I said, I mean, this is just one case, right? In this is a huge field. So there are a couple of points. The first point is that this is a huge field. A lot of world leading experts are working for more general kernels. So that's the first point. And you know, there are wonderful review and lecture notes and monographs in this field. They're quite accessible. So if someone want to get into that, I can send you some. That's the first point. The second point is that physicists typically they do scaling analysis. When they do scaling, they see that one of the important case of for A is this scale with A S hat equals to S times S hat. And this satisfies the scaling analysis, and it's important in the polymerizations problems. And similar for B, when B equals to 1 is also corresponding to an important scaling analysis problem. And I chose it because this is becoming, then it becomes a critical case when the two are of the same size. And yes, I have some other cases. For example, if A equals to S times S hat to some power, and B equals to some other things, and they are also critical. And in that case, after doing transformation, I have the fractional Hamilton-Jacobi equation. It's even harder. So they are there, but I have not been able to finish this problem. So my goal is to finish this problem first and then go to understand more general cases. So that's why what I said, this is the beginning. But you know, sure. I mean,
Yeah, thank you very much for your answer. So because I think the function is like the variable are separate. So yeah, maybe.
Yes.
Yeah.
I need. Yeah.
So in the formula. Yeah. Okay. So thank you very much. Is there any question? Okay. Is there no? So let thank speaker again. So I hope that we sometime we can meet you in person in Vietnam, and some people here can become your student.